All right. Good morning, everybody. Let me go ahead and start the my timer here, and then I want to get started with this. Yeah, unfortunately, like I said, I still had some issues with my my computer. So obviously, you can tell right now. No, there's no video. All I can do is record on audio and save this. And so, hopefully, this works. And what I'm going to try to do is I'm going to try to see if I can fix this problem here. But if not, in the meantime, I'm just going to continue to record the lessons here, and all we'll have is the audio version of the lesson. But I think we'll make it work. So I apologize for not having the lesson ready for you on Friday. What we're going to do then is we're going to go over really quickly what I went over with you on Thursday in regard to the sigma bonding, and so we'll review that really quickly, which is what you see on your screen right now. And then what I'd like to do is talk about the pi bonding, and then I want to go ahead. I want to talk to really quickly about how we can summarize what we've done up to this point, and then we'll get into the discussion of VSEPR theory. Okay, so that's what I would like to do, and hopefully by the end of the lesson today, we can go ahead and finish up with the discussion of bonding, of covalent bonding, and then get started into the discussion of intermolecular forces, the intermolecular interactions, and try to wrap that up by tomorrow. So that we can leave on the break without having to worry about learning anything new. Okay. All right. So with that said, let's go ahead and let's talk about the bonding. So there are two types of interactions, bonding interactions. So we refer to these as bonding interactions. And so we have sigma bonding interactions and pi bonding interactions. I left off on Thursday. We finished up with this idea of sigma bonding interactions. And remember, with the sigma bonding interactions, what we have then is that the orbitals, either they will be hybrid orbitals that overlap with one another, or we'll have a mixture of atomic orbitals and hybrid orbitals overlapping with each other. But this overlapping of the bond of the orbitals that lead to sigma bonding is a specific type of overlap, where the overlap, when it occurs, will form a new type of bond, which interaction, which we won't talk about in this class. But essentially what you have to make sure you understand is that the sigma bonding interaction, the result of it is that we have a symmetrical bonding interaction, which essentially what we have is we can draw a straight line through. Okay, they are the sigma, the interactions between the orbitals then is symmetrical, where it's symmetrical along a straight line. So you can draw essentially a straight line through the bonding interaction. So I want to go ahead and give you some examples here as a way to review what sigma bonding interactions are. Okay, so understand this. Well, when we refer to sigma bonding and pi bonding, these are interactions between the orbitals. These are not orbitals themselves. So we talked about the atomic orbitals. We talked about the hybrid orbitals. So when we discuss sigma bonding interactions and pi bonding interactions, we're talking about how these orbitals interact with one another to form these bonds. Okay? The orbitals themselves are not the bonds. But the interaction of those orbitals, that's the bonding that we have. Okay. All right. So with that said, then let's take a look at one example here. Okay. So here we have then the bond, you can imagine, that between two hydrogen atoms. Okay. It's a single bond. Okay, it is there is no hybridization here. This is just two s orbitals. So the hydrogen atom on the left, the blue hydrogen atom, the yellow hydrogen atom on the right, they interact with each other. They take their s orbitals and they overlap. Okay, and that overlap then occurs down a line. So if you can imagine, then let's go ahead and let me go ahead and draw in the. Let me go ahead and open up my pen here really quickly. You can imagine that there is a line of symmetry, or you can imagine just a straight line that runs straight down through the center of each one of those. And because we can draw that straight line right down the center of those two atoms, when they overlap in this manner, we refer to that then as a sigma bonding interaction. So this interaction here between two s orbitals, now understand, these are two atomic orbitals. They can overlap in this manner. And so this single bond here, so what we're referring to here is a single bond between these two atoms here. So this single bond, so this is a single bond. Sorry, pen is not working again. The single bond, okay, is a result of sigma, and this is the Greek letter sigma bonding interactions. Okay, and that sigma bonding interaction then okay, is a result of an overlap here between these two s orbitals. Okay, and again, these two s orbitals will form only a single bond because remember it's a pair of electrons that are paired shared between these two atoms here, and so this is a single bond because two electrons are being shared. This is a sigma bonding interaction because when they overlap with one another, these two orbitals here, you can draw a straight line through them and they will basically revolve around this straight line here. Okay, so that's why this is a sigma bonding interaction. So that's one example of a sigma bonding interaction. Again, these two sigma, this interaction here is the result of two atomic orbitals, two s orbitals here, overlapping with one another. Okay. Another type of interaction is, and we're using atomic orbitals again, is the interaction between two p orbitals here. Okay, and if you notice, then this is also a sigma bonding interaction because if you take a look at this here, you can draw a straight line, again, straight through, and you can see that. Now, with this particular type of interaction, it's not necessarily a single bond, but it is an interaction between two p orbitals, okay? And so they are sharing a pair of electrons here as well. But typically, we see this type of overlap here, well, in double and triple bonds. Okay, so we'll see this type of overlap here in double or triple bonds, okay? Now, typically, I mean, that's where we will see them, okay? But typically, we won't see this type of p orbital overlap very much. Whenever p orbitals p orbitals get together, we typically see them in a pi bonding interaction. But if they overlap in this manner, this then would be a sigma bonding interaction as well. Okay. So again, if the p orbitals do overlap in this manner here, and the two electrons in these p orbitals here do overlap, and you can draw a straight line through them, and they are symmetrical through this straight line, this is a sigma bonding interaction again. Okay, and the result of this overlap here would either be a double or triple bond. We'll see that we won't see this. We will typically see a double or triple bond form from a pi bonding interaction. And we'll talk about that in just a moment. Okay. All right. So we saw then a sigma bonding interaction between two s orbitals, between two p orbitals. We can also have a pi bonding interaction, and more typical pi bonding interaction between two hybrid orbitals here. So you can imagine then this could be two sp3 orbitals. This could be two sp2 orbitals. This could be two sp orbitals here. But if the hybrid orbitals interact, and I'm just going to arbitrarily say here that these are two sp3 hybrid orbitals. Sorry, let me go do this here. So this is going to be sp3 hybrid orbitals. So we have one sp3 hybrid orbital here. So this is one sp3 from one atom. This is another sp3 from another atom. And if you notice then, when they overlap in this manner here, again, we can draw a straight line running straight through the center both of those hybrid orbitals, and I'm sorry, it's kind of a little bit off here, okay? But because of that, then we see then that there is an overlap. And whenever we have an overlap of sp3 hybrid orbitals, remember what we have then is a single bond. So a single bond then forms when sp3 hybrid orbitals overlap, okay? And the overlap in this manner here then is a sigma bonding interaction. Okay, because again, we can draw a straight interaction, okay, a line of symmetry through that interaction. Okay, so single bond then, single bond resulting from a single bond results from a sigma bonding overlap, okay, interaction here. Okay, so there we have then two hybrid orbitals that are overlapping. Okay, and then the last type of sigma bonding overlapping that we're going to see then is an overlap between a s orbital, okay, an atomic orbital, and a hybrid orbital itself. So you can imagine then we have here an overlap between an s orbital. So this is an s orbital from, let's say, just a hydrogen atom. We have an s orbital from a hydrogen atom right here. Let me go ahead and draw this in here. So we have a hydrogen atom. This is an s orbital. So this is an atomic orbital, and this is a hybrid orbital. So we can imagine then this being an sp3. Okay, and so with that said, then if we have an overlap between an s orbital and an sp3 orbital, that also will be a sigma bonding interaction. Okay, so again, we can draw a straight line through both of those orbitals there. Okay, and so you can imagine this then also being then a single bond. This is typically how a single bond forms between hydrogen and any other atom. And this is also going to be sigma bonding interaction as well. Okay. All right. So with that said, then, if we take a look at this, and these are the types of interactions that we have, okay, between different orbitals and how when they overlap. Each one of these, though, will form then a sigma bonding interaction. Okay, so let me go ahead then and save this really quickly. Oops, sorry. Go ahead and save this really quickly. Okay. Okay. All right. So with that said, just keep in mind then the different types of the different ways that sigma bonding interactions can form here. Okay. Because let's go ahead then. Let's take a look at the next type of interaction here, and that is going to be then the pi bonding interaction. Okay. Now, the sigma bonding interaction results from two orbitals lining up. And you can imagine lining up along a straight line, okay, with the pi bonding interaction. Then what we're going to see then is two orbitals lining up so that they are side by side with one another, not along a line, but they are side by side. And if you take a look at what we have here, we have the two p orbitals. And if you saw them, remember in the previous slide, the two p orbitals then if they had formed a sigma bond, if they were kind of lying down on their side, and so they can line up. Here, if you notice, and the term standing up kind of works here. You notice here the two p orbitals are pointing vertically, okay, but they are side by side with one another. They are not falling along a line. And so when you have that side by side interaction right here, and what you're going to notice, and when we have that side by side interaction, okay, let me go ahead and point this out here. What happens then is that when they draw closer and closer together, they start then their atomic orbitals start to overlap, okay, so that now you have then the top portion here, if you can imagine this then, okay, the top portion here forming this this top region here, and the bottom portion here forming the bottom, the two bottom lobes here, forming the bottom region over here, okay. This is what we refer to as the pi bonding interaction. Okay, so these pi bonding interactions, and this is what you need to remember, we typically see these pi bonding interactions result from a two p orbitals, taking two p orbitals and overlapping with one another. That's typically how pi bonds form. Okay, and so the electrons then can move between the upper region here and the bottom region here. The electrons can move between both the top region, and sorry, let me go do the top region here and the bottom region. Okay, and it works pretty well that way, is to help also explain or also adhere to the Heisenberg uncertainty principle, where we're not quite sure where the electrons can be located at any time. All we can say then is that they can either be on the top lobe right here or the bottom region here. Okay. So with these pi bonds, then what we also see then is these will typically be found. These pi bonds will be typically found as part of a double or a triple bond. Okay, so in a double or triple bond, okay, the 1 to 2 of those bonds will be either a pi bond. Okay, so the pi bonds typically form then, okay, when you have a double or a triple bond, and the remaining bond then is going to be a sigma bond, and we'll see that when we get to in just a moment when we get to the VSEPR. Okay, all right. So with that said, that's what we have then with the pi bonding interaction. So what we have to make sure we understand then is that we have then an overlap that occurs on a side by side rather than an end-to-end basis. Okay, so keep that in mind as we go through with this. Okay, all right. So let's go ahead then. I'm going to go ahead and let's take a look at some examples here, okay, and to help you kind of better understand the difference between sigma bonds and the pi bonds here. Okay, let me go ahead and let's move on to the next one. Okay, let's look at some examples here. Let's draw some structures here, and let's take a look at this. Now, what we're going to be doing here is we're going to be doing what's called describing the molecule. Okay, now that when you are told, or when I'm asking you to describe the molecule, and let's make sure I point this out to you. Okay, so when we are discussing this, when I'm asking you to describe the molecule, okay, what I'm asking you to do, okay, is I'm going to ask you, and the instructions then will ask you to describe it. Okay, so when you're describing a molecule, what you will be doing then, okay, let me go ahead and write this down for you so you can remember. Okay, first, what you will do, whoops, sorry. Okay, so when we describe a molecule, you will describe the bonding type, the type of bond, okay, and that is then describing whether it's a single, double, or triple bond that that is being shared between the two atoms. Okay? Now you can typically do this by simply just drawing the Lewis dot structure. You can identify the bonds, okay, by simply drawing the Lewis dot structure, Lewis structure. Okay, so that's what you can do. So that's the first thing you want to do. Then, as part of the description, what you want to make sure you do then is identify the hybridization. Oops, sorry. Oops, sorry, hybridization. That is, if there is any hybridization that occurs, okay, you need to be able to identify that as well, okay? And then you need to also describe the bonding interaction. So not only the bonds here, but you have to describe the bonding interaction, and that's what we just talked about there, which is going to be then either the sigma bonding interaction or the pi bonding interaction. Okay, so that's what you have to do for the bonding interaction. And then finally, you have to describe the geometry. Okay, you have to describe the geometry of the molecule. So the Lewis dot structure here, okay, so when you draw the Lewis dot structure, that's simply a two-dimensional drawing. So here then, you want to describe then the three-dimensional, it's a 3D drawing, okay, three-dimensional description. Okay, and for example, then tetrahedral would be an example of a three-dimensional geometry. Okay. Okay, and so when you're asked to describe the molecule, a molecule, you would need to be able to include all four of those descriptions. Okay, and so let me go ahead and save this, and I will post it for you. But make sure then that you keep that in mind. Okay. All right. So let's go ahead then and let's describe these two molecules. Okay, so let's go ahead and first of all, let's draw the Lewis dot structure for carbon. This will give us a chance to practice a little bit. I'm sorry, carbon, methane here, CH4. Okay, so carbon then, it would be the center atom. Remember, with carbon, it's always going to be the center atom whenever you see it. And from now on, like I said, I'm going to draw then. Hopefully you recognize then why each one of these here will be a hydrogen bond, hydrogen interacting with a carbon in a single bond. Hopefully you recognize that, please. If you do not recognize that, if you can't see how we draw the structure, you need to come by today. Come by after school. I'll be available and on Zoom and get your questions answered. Okay. All right. So with that said, then let's go ahead and describe it. So there's the Lewis dot structure. Okay. So obviously we have single bonds here. So let me go ahead and label that for you. So we have then each one of the atoms here. Whoops, sorry. Each one of these atoms here are held to the carbon. Each one of the hydrogen atoms are held to the carbon atom by a single bond. So let's go ahead and do this. So the first description then is that each one of these here, and I'm just going to go ahead and highlight two of them. These are then single bonds. So there it is. We have described the bond, what type of bonds we have here. And there are only single bonds here. So that's the type of bond that we have that holds these four atoms to the carbon. Okay, and remember, single bonds then, two electrons are going to be shared. Now, what you should also remember to include then are the lone pairs, but obviously carbon, methane here has no lone pairs. It uses all of its electrons to bond. Okay, so no lone pairs, and don't forget to include the lone pairs as well. Okay, all right. So next thing then, we want to discuss the hybridization. Okay, now understand hybridization, and you got to make sure you remember this. Then single bonds. Whenever you have a single bond, and we talked about this. Okay, the hybridization on a single bond then is always going to be sp3 hybridization, and this is something you have to remember when we go through this. Okay, so if you don't remember, please go back and review that. Okay, so the hybridization here for all four of these bonds then are going to be sp3 hybridization as well. Okay, so the hybridization on all four of these